Okay, so we are looking today at so this is going to be day 5 where we're not necessarily going to go through anything new per se, although there will be some new information. But we're going to review everything. We're going to talk about the NASM's chapter 2 today. So this is the chapter 2 that's in your textbook. And this is basically where we go over the whole kinetic chain. And the kinetic chain is going to be the muscular system, skeletal system, and nervous system. And there's just a little tacked on endocrine system like paragraph at the end. So just a very, very small bit. So today we want to kind of understand the fundamental concepts that relate to defining the structure and function of the kinetic chain. We want to understand our anatomic structures. We want to understand our physiologic functions and how like all of that works in order to produce like human movement, right? So by the end of this, we should be able to understand sort of those 3 main systems, plus a little bit of the endocrine system, and how they kind of respond and adapt to exercise. So this is where we get our first kind of look here. We'll often call it the human movement system. So the human movement system, or more commonly referred to as the kinetic chain. That's oftentimes what most people call it, is going to be a series of interdependent systems consisting of the muscular, nervous, and skeletal systems, right? So these 3 systems work together to produce and control human movement, right? So the big thing that we need to remember about this, right? Like that's their main job. Is like these are the 3 systems that are related to us like moving around. Now, you've also got like your energy systems, right? Which is basically how your digestive system and your respiratory system works together. You've got your cardiorespiratory system, which is how your cardiovascular and your respiratory systems work together. But this one, those are all like support systems to kind of keep our body alive. This is the system that's responsible for movement. So when we're looking at like how to produce efficient human movement, you know, posture and things like that, we need to have an understanding of how the kinetic chain operates, right? So all components must work together. Must work together to produce movement efficiently. If one or more segment is out of alignment, it will affect the other segments. So this is why it's actually called, this is why it's called the kinetic chain actually, is because it is kind of like a link. It's like a series of links in a chain, right? Like if you think of a chain there and you have like one link that's like slightly malaligned, it's going to screw up the other ones, right? So that's where that's why we use that term so often. So kinetics is going to come from the word forces, and chain is something that is linked together. And if, you know, one link is weak, then, you know, the rest of them are going to be weak. So if your muscular system is, you know, in a shortened state because maybe it has scar tissue or something like that, that's going to teach your nervous system how to control that muscle the wrong way. And then that's going to pull your skeletal system out of alignment. And so then maybe you're going to experience some like rubbing or burning sensations, you know, inside those joints. If your joints are out of alignment, that's going to cause your muscular system to not be able to move the way that it's supposed to. And then again, your nervous system's not going to be able to recruit muscles strongly, and so you're going to get a weak contraction. Or if your nervous system doesn't know how to do a movement efficiently, or if it's learned how to do a movement inefficiently and it's gotten used to that, likewise, that's going to move your muscular system the wrong way, and then that's going to move your skeletal system the wrong way. So it's all kind of interconnected there. So let's go ahead and quickly go through, we'll go through these again, each of our systems. We're going to start with the nervous system today. It's going to go in a slightly different order than how we did it before, but the nervous system, right? Again, this is going to be one of our main organ systems, and it is a system containing specialized cells that coordinate signals, and this is the important part here, provide a communication network throughout the body, right? So I just knocked my mouse right off my my little platform here. Uh, so that's our nervous system. Yeah, sorry, that was probably really loud. Um, so that's our nervous system, right? It's there to like provide communication throughout. It's getting information in and it's sending information out in response. So again, it's going to be comprised of two primary sections. Right, that's going to be your central nervous system and peripheral nervous system, right? I should say it's your PNS because sometimes they'll put question, they'll sometimes abbreviate in the homework questions. That's your CNS and your PNS, right? So those are your two primary divisions, right? The peripheral nervous system communicates with the central nervous system. Central nervous system makes all of the decisions, right? So central nervous system, like we said yesterday, it's your brain and your spinal cord, and your peripheral nervous system is all your cranial nerves and all of your spinal nerves running throughout the body. So there's that communication network that we're talking about. Now, one thing we didn't spend too much time talking about yesterday is that your nervous system has three primary functions. So when we're looking at like the functions of your nervous system, right, we're going to see that it has sensory function, right? It's going to have integrative function, and it's going to have motor function. And so this kind of goes in order as of what we would think how the nervous system works, right? Like you would sense information coming in, your brain would integrate that information with a response, and then it would execute that response using motor neurons. So like, let's say something information comes in, like you touching a hot stove, right? That sensory information goes to the brain, and the brain goes, okay, well, how hot is it? If it was this hot last time that happened when we were like 3 years old, we remember this like, holy crap, that's really painful, so we moved our hand away. Is this like that? And then it's going to run its data and be like, yeah, it is like that. Okay, holy crap, let's move our hand away. And so then it's going to execute the motor response back in the opposite direction. So that's sort of what we're looking like there. But even in the terms of like learning how to exercise and move, right? When you're moving through like a full range of motion, like a squat, for instance, right? What's going to happen is like all of these sensory neurons running throughout like your glutes, your core, your quads, hamstrings, calves, the bottom of your feet, right? All of those are bringing sensory information up to your brain, and your brain's like, okay, how well are we descending into this squat? And then like, let's just say, for instance, you're doing it with bad form. And so maybe your hip isn't aligned improperly, and so you start to feel like a pinching sensation in your femur, right at your hip. You're impinging your hip there. Well, you've got sensory information going up to the brain that's like sensing that, and so now your brain is going, okay, so we're descending into a squat, and I can kind of feel this pinching sensation. I should adjust the angle of the leg to reduce that pinching sensation, right? So there's the integrative function, like a decision is being made about like how to continue moving. And so then it will execute a motor response by maybe adducting or abducting or internally rotating or externally rotating that leg in response. And so you adjust your form like midway, maybe your foot turns slightly, something happens. That's the motor response that we're experiencing. So let's go ahead and look at those like sort of more in depth here, right? Sensory function by definition, we're going to define that as the ability of the nervous system to sense changes in either the internal or external environments. So it's not just your internal environment that this is happening to, right? Some of this sensory stuff you're not even noticing. A lot of it is actually a big part of your autonomic nervous system, right? That's stuff you don't really have any control over. Sensory information is still coming in related to that as well. For instance, like, if anybody for those of you who've already had breakfast this morning, right? Like that breakfast is moving through your stomach, and there's stretch receptors at the very end of your stomach. And once food is broken down enough to like the right consistency, those stretch receptors get triggered to open your stomach up and let food into your small intestine. Meanwhile, if something is like too chunky and not really broken down enough, and it passes over one of those stretch receptors. That causes the stomach to close down and continue churning in order to like continue to digest that food. So you've got sensory receptors happening constantly throughout your body, sending information to the brain so the brain can interpret that. Not everybody has like perfect sensory receptors, you know? A lot of times, like when you know somebody who tends to be like a little more sensitive when it comes to like, like physical sensations and things like that, they have different sensory receptors than someone else. And this is why some people actually do have like a high pain threshold and like a low pain threshold. I know that like, because I've like pulled my right hamstring so many more times than like my left, it's kind of funny. My right hamstring is definitely not as flexible as my left is. And if I go get like a massage, like massages are always like a love-hate relationship. You're like, oh, it hurts so good. Oh my God. Like they're like, bring up that scar tissue. Oh, like, but what's funny is like when I stretch my right hamstring, I'm not getting as much range of motion out of it as I would in my left hamstring, but my left hamstring feels way worse. Like when I'm doing it, I'm like, oh God, stretch you mother, like, and it's funny because it's like, you would think that the more immobile of the two would be the more sensitive one. But the thing is, like, I'm used to pain on that right hamstring. Like I'm used to that right hamstring kind of being tight. And so my nervous system has come desensitized on one side, but it's still kind of fresh and raw on the other side. So when I stretch, I feel everything. And that's where like sensations come from. And we'll talk about like how to turn those sensations off here in just a little bit. But that's sensory function, right? So good examples of sensory function are sensory receptors. A good example, well, actually, I should say example. Right, sensory receptors sense the touching of a sharp object, right? And then you've got your integrative function. So your integrative function is the ability of the nervous system to analyze and interpret the sensory information to allow for proper decision making and the production of an appropriate response. So your integrative function is your nervous system's ability to go like, hey, that's really sharp. We should not keep touching that, right? Or the integrative function is like it's kind of fun. I don't want to stray too far into this, but there's a lot of like integrative function that we just inherit. Hold on. And the production of okay. Like there's a lot of inherited integrative function, I think. Like either of you guys, are you afraid of spiders?
Yes.
Yeah. So it's kind of funny. It's like, where does that come from? Like, did you have like a horrible experience with spiders at one point in your life?
I don't know. I was just always scared of them.
Yeah, totally. Right. Well, chances are like you come from like a group of people that lived in a place where like you need to stay away from those spiders. Like, like me, like I grew up in the Northwest. And there's lots of spiders out there and stuff, but I mean, and lots and lots and lots, because it's like a wet, swampy, area. But like, they're not really all that, none of the spiders out there are dangerous. I moved here to LA and we got black widows, but I grew up like not being afraid of spiders. Like, however, when I was a kid, I'm horribly afraid of bees. Like it's the scariest thing in the world. And people always go like, "Oh, are you allergic?" And I'm like, "No." Like, I just don't like how they fly. Like it makes me uncomfortable. Like I don't like this. This freaks me out. This is fine. Like, and so like I kind of don't like hummingbirds either, which is really weird. Like it's not that I'm afraid of hummingbirds, but when I see them, people are like, oh, and I'm like, ugh. And I'm really kind of weirded out by drones, which is like a weird thing nowadays as well. But stuff that hovers just kind of freaks me out. And so there's probably like some type of thing in like my inherited instincts, right? That has like integrative function to be like, no, stay the hell away from that thing. And it's interesting, your integrative function has like a lot of instinct. But aside from that, I think that's a fun topic. It isn't directly related to what we're looking at, but that's like your inherited integrative function, you know, like babies who naturally know how to hold their breath if you drop them into water, you know. That's
Yeah.
like an example of that. But the more classic example of what we're talking about is just taking old information and using it to understand new information, right? So like you'll notice, if you ever do like one of these things where you ever see those, you ever see people sell those bracelets with like the copper, like the copper in them, and they're like,
Yeah.
if you hold it, it'll give you better balance. You know, they were so popular
Yeah.
like 10 years ago. And so what you do is, you know, they make you do this test where you hold, you know, you stand up like this, and then they pull on one of your arms, and you're like, and then you have to put your foot on the ground, and they're like, see, you had bad balance. And then it's like, okay, now hold on to this bracelet. And then they'll push again, and you'll resist it and be fine. That has more to do with integrative function. Like your brain knows how to do the movement. Like that has a lot more to do with like, yeah, I didn't know how to do it the first time. Let me take another crack at that. And that's how we get better at stuff. We take all that sensory information and we interpret it better and better and better over time. So an example of this, right, would be like if you have sensory receptors that sense the touching of a sharp object, anytime you've ever touched a sharp object in the past, you've learned that like that causes damage to your skin, it causes damage to your muscles, it causes nociceptors, which are your pain receptors, to trigger. And so since the integrative part of the nervous system let's see here, understands and interprets the sharp object as something to avoid. That's a pretty good way to put it, I guess. And then you are going to, and then you're going to have your motor response, right? And motor response is the neuromuscular response to sensory information. So this is where we see the term neuromuscular, right? This is where like the nervous system is integrating with the muscular system, right? Like your sensory function came in, integrative function figured it out, and then your nervous system can't be like, okay, well that's really sharp, and then move it away on its own. Your nervous system can't contract. So it has to outsource the moving part, the job part, to your muscular system and say, okay, well, muscular system, let's recruit that bicep and, you know, squeeze that arm away. And so that is like an example of that, right? Is motor units are recruited to contract muscles and draw the hand away from a sharp object. So those are three of our main things. Now, all of that kind of, you know, it's pretty easy to understand, right? It's like a loop. Step one, you sense something. Step two, you figure out what's going on. Step three, you produce a response. But what's really cool is all of this is happening super, 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 super fast and constantly in real time at like lightning speeds. And it's happening in order for your body to understand where it is in space. It's not always about a sharp object. Sometimes it's just about like interpreting how much gravity is pulling down on a certain body part. So this is where we have to understand a concept called proprioception. I would argue if you forget everything from today's lesson, this is the one thing that you should remember. Proprioception is the most important term, I would say, on today's lecture. And that's hard to say. You know, it's like picking your favorite child. But like, I would say if you'd forget everything, I'd say remember this one. Okay, this is a big part of our nervous system. So proprioception is the body's ability to sense the relative position of adjacent parts of the body, right? It is and this is going to be like kind of a weird, highly technical definition, but it is the cumulative neural input from all proprioceptors throughout the body It's all the information coming in, and it's all of your body's ability to sense its position. So here's my favorite way to kind of explain this. If I take my hand back behind my head and I start wiggling my fingers, how do I know that I'm actually wiggling my fingers? Now, immediately somebody goes, well, you're telling your fingers to wiggle. Like,
But
how do
you
you
can
know it's
kind of
happening?
feel them,
You're,
right?
you're the one telling it to happen. Of course you know it's happening. Okay, great. I hear what you're saying. I love, that is true. I am telling it, so of course it should be happening. How do I know it is happening?
What the heck?
Right? Like, how do I know it's actually occurring? Right? Like, yeah, I'm sending information away, but how do I know it's listening to me? Right? Like, I could tell someone to do something. How do I know it got done? Like, I could, I constantly tell my parents to eat better. How do I know if it's happening? If they don't send me pictures of their meals, they don't do that, but I would never make my parents do that. Even if I did, they wouldn't. Thought I was rebellious as a teenager. I'm sure my parents are gonna be worse. So like, that's how do I know it's actually happening? Well, that's where you have stretch receptors and things like that. You have what are called proprioceptors. We're going to more commonly refer to them as just sensory receptors, but those sensory receptors are what allow your body to, there's information going out, which is being recruited like with the motor units, but these sensory receptors are sending information back to the brain. And what's fun, but also very frustrating, is they are not always telling the truth, which we'll get to in just a little bit. But that's what proprioception is, right? So what I've got when I say that I'm wiggling my fingers, right, I'm sending a signal away to make it happen. But I've also got stretch receptors, I have got pressure receptors, and I've got tension receptors, all running throughout like my entire hand and all of my other muscles throughout my whole body. So stretch receptors are sensing how long something is, like if it's stretched out or if it's relaxed. Tension receptors are sensing like how hard something's pulling on a bone or how relaxed it is. And pressure receptors are sensing like what the pressure changes in a joint might be as it moves through a range of motion. So one of my favorite ways to understand proprioception is to use what I like to call the duck analogy. The duck analogy is this. If I told you that there's an animal in a paper bag, and you have to guess what animal it is, and I told you this animal has webbed feet, feathers, a bill, it quacks, and it likes to lay eggs, right? You're going to take all that information and you're going to run it past like all the info in your brain. You're going to be like, okay, birds lay eggs, right? Ducks quack, it's a duck, right? Like you're going to like figure it out by running it past information. Well, if a stretch receptor is being pulled, this much, and a tension receptor is being is at this much tension, and a pressure receptor is at this much pressure, then my finger is in this position. That's how my brain understands that. And if those numbers were different, then my finger might be in this position or that position or this position, right? Like all over different positions. Like how does your brain know that you successfully bent your elbow? Because this muscle is now shortened, this muscle is now lengthened, and the pressure in the elbow has changed. Does that make sense?
Batman and Robin.
What's that?
Batman and Joker.
Yeah, Batman and Robin, right? Like, and that's actually like a thing. Like when I mentioned earlier, this is how it's supposed to work, but we often have altered proprioception. Like a lot of times, like we have, like when you have poor posture, that is because you have altered proprioception. Your brain has learned that this altered position that you're in is now your new resting position. And you're basically getting false information from these proprioceptors. And that's what happens in certain things where like maybe Robin starts doing more work than Batman. Like Robin's gone rogue and he's doing all the work now and Batman can't do his job anymore. That's actually like why my hamstrings pull all of the time. My hamstrings like to do more work than my glutes do. My glute is meant to be the main Batman, right? And my hamstring is there to help. But your hamstrings can do the same motion. Like your glute's in charge of what is called hip extension, right? That's this. But your hamstring does a little bit of weak hip extension as well. It's just not very good at it. But if you use your hamstrings too much, which I tend to, right, what ends up happening is they start to take over, and then your glute can't do its job, and you end up with altered proprioception. And then you end up with posture like mine, which is where my butt actually kind of tucks underneath my body like this. This is an exaggeration, but like most people have like that kind of exaggerated low back arch. I have the opposite. I have like a flat back posture, which is not something that you want. You want to have like a neutral posture. But the reason is because like the proprioceptors in my hamstring, they're sending a signal to my brain saying like, yeah, we're at full length. We can't stretch any further. And then my brain believes it. But if I stretch my hamstrings, all of a sudden I get all this extra range of motion and I get, back to a neutral posture. Hopefully that gives my brain the ability to be like, you're lying. And then it learns its proper posture again. So this is why understanding this is such a big deal, right? Like when we understand these proprioceptors, we understand like how our body is able to, produce this movement. So movement is nothing more than a response to sensory information. And that's why like movement is completely dictated by our nervous system, right? And that's why it's so important for us as trainers to train our clients in what they're saying here is a multi-sensory environment. What they mean by that is just they'll sometimes say like a proprioceptively enriched environment. What they mean is like a wobbly environment. Like you should be training your client in a situation where you might take something like unstable and you're going to stand on it and then you're going to do your bicep curls like that, right? Like now that I'm standing on this thing, I've got all this sensory information coming in. I've got so much extra sensory information. So I'm learning how to do a bicep curl in this position and this position, like as I'm slowly like stabilizing. And that's going to help me develop more proprioception because I'm giving my brain more information, right? Like your brain learns stuff through experience, right? It touches a sharp object and goes, holy crap, that's sharp, right? Then the next time it touches a sharp object, it remembers and goes, okay, I'm not going to poke that thing, at least not as hard. So the most effective way to create these long-term effects is to properly, work with our nervous system. So that is proprioception in a nutshell. Like I said, this is arguably the biggest concept of the day. Now, we are going to see our neuron again, right? So looking at neurons here, right? Remember, we said this yesterday, is the functional unit of the nervous system. Just like the muscle fiber is the functional unit of the muscular system, the osteon is the functional unit of the skeletal system. So the neuron is the special like shaped thing, the special shaped thing that allows this communication to take place. And so in your neuron, again, looking at the same thing we had yesterday, we see our cell body, right, which is going to be the main portion of a nerve cell that can a nervous cell that contains a nucleus, mitochondria, lysosomes, I guess I could say. I'll just say and all other normal organelles. Right, so you can see all the normal stuff in the cell body. Like there's nothing, it's still a human cell, even though it is specially shaped. But the two things that make it unique is that it has an axon, which is the tail, right? And that provides communication from the brain or spinal cord to other parts of the body, right? So the tail of the neuron that sends signals away from the cell body and synapses with other tissues, right? So your axon is really the tail that like grabs something else, right? If this analogy like barely works in this world because we all have freaking cell phones, but like basically this is where you plug in your old phone line. That's the axon of your phone. Oh man, I went full boomer there. Then we've got our dendrites, which are going to gather information. Gathers information from other structures of the body, right? So the dendrite is going to, the fingers of the neuron that gather information and send it towards the cell body. So your dendrites are going to like gather that information. It's going to run in, and then it's going to head down the tail, right? Like if I looked like a neuron in like a Y shape, right? I'd gather information from here, or maybe I'd gather it from here. It would come to my center and then head straight out the tail. And then it would synapse with another neuron. So that is what's kind of cool there. So that is where we look at our three main types of neurons. And I already got these in your notes yesterday, but I know we kind of have to mention them again here real quick. So our three types. Oh my God. Speaking of typing, we got sensory neurons, right? Sensory neurons are neurons that transmit afferent impulses from receptor sites to the brain or spinal cord. So your sensory neurons are in charge of gathering the info so that your sensory function can exist, right? Then you got motor neuron. I'm actually going to do this in a slightly different order. We're going to do interneurons second. Interneurons, which are neurons that transmit impulses from one neuron to the next, right? And then we have got motor neurons, which are neurons that transmit efferent nerve impulses from the brain or spinal cord to an effector site such as a muscle or organ, right? So motor neurons are going to be the ones that like are going away. So you've constantly got info coming in, you've constantly got info going out. And that's what we're seeing there. Sorry, I'm so distracted by like all the stuff that's happening like outside my window, but there's just a lady who's just whacking a plant. She's just standing there. She's been at it for like 5 minutes. Or it feels like 5 minutes at least, but she's just going like this on this random plant outside my window. That's so weird. All right. So that's very much like the types of neurons you've got. So sensory neurons, interneurons, and motor neurons. So we go. Let's go through like a sensory neuron. Let's say you're standing on one leg, right? And then you start to tilt in one direction, right? Sensory neurons are going to go to the brain, and the brain's going to go, oh, we're tilting, right? And then it's going to recruit the appropriate muscles to get us back to neutral. And so it'll be a sensory neuron. We'll find out the information. Then it will go from interneuron to interneuron to interneuron until eventually it gets to the brain. The brain will interpret that information, and then it will say, okay, here's the response. And so then it will go from interneuron to interneuron to interneuron until eventually it hits a motor neuron and executes the appropriate response to get you back to neutral. So your central nervous system, again, that's going to be your brain and spinal cord. That is going to be the central decision maker. Then you get your peripheral nervous system, which is going to be all of your peripheral and cranial nerves, right? So look at all these different like nerves like running off from your body, like all these different pairs, right? And you'll notice like you get a pretty big, interesting like complex here. You know, a lot of those are in charge of like controlling your body's organs and things like that. Then there's a bundle down here that it would actually travel down your leg. That's where your sciatic nerve is at actually. And it controls everything running down, which is why if you ever know anybody who has sciatica, they get that pain that shoots down their leg or that burning sensation that runs down the leg. So your peripheral nervous system is going to be divided, just like we talked about a couple of days back, where it will be divided into a couple different sections here. So if we're looking at the divisions, of the nervous system, right? It's going to be your central and peripheral, actually central nervous system, and then you have your peripheral nervous system. That will divide into your somatic nervous system, which is going to be the voluntary system. And then you're going to have your autonomic nervous system, and that is going to be the involuntary system, right? So somatic is like when I tell my muscle to squeeze, that's somatic, right? I have control over it. I have conscious control. Autonomic is stuff I don't have, right? Like when I squeeze that muscle, if it increases my temperature, and so then my entire hand gets, my arm starts to sweat a little bit in order to cool that section of my body down. That's autonomic. I don't have any control over my sweat glands, right? But both of them are response, right? Like my somatic nervous system was recruited because my brain produced a motor response. My autonomic nervous system was also recruited because my brain produced a response. But in this case, it was autonomic because my peripheral nervous system, sent motor neurons that squeezed my sweat glands and opened them all up, right? And opened up my pores. Both are being under the control of the nervous system, but one is like a different type of function. And then the autonomic nervous system is split into two different versions, right? It's going to be split into the sympathetic, which is the fight or flight system that we mentioned, right? So like sweating, for instance, is an example of a sympathetic reaction because that's like sort of a panic reaction, right? It's like, oh, we're hot, cool down, And then we have the parasympathetic, which would do the exact opposite. Like once I'm done exercising, my parasympathetic would be the rest and digest system, right? That's going to say, okay, we don't need to use any of that heavy duty stuff anymore. We can go ahead and relax. Let's relax and turn the digestive system back on, And that's what's kind of cool. Like we talk about some of the positive effects of like blood pressure that come along with exercise, right? So blood pressure is super important to maintain at normal levels because that's how your body effectively moves blood around. When you start exercising or when you start walking, like when you get up in the morning, all these different things start to happen. Like your skeletal muscle is officially needing to be used. And so because you're using it, it needs to produce energy. And because it needs to produce energy, it needs oxygen. And it gets oxygen by your blood is what delivers oxygen. So when you start like recruiting muscle, your body goes, all right, let's improve blood flow to the muscles. And so it'll open up blood vessels that go to skeletal muscle. Like as you start to like run up a hill, the blood vessels in your legs expand like crazy. This is why you get really vascular when you're lifting weights. You'll notice your veins kind of pop out of your skin.
Yeah.
That's what's happening there. That's an increased blood flow to those types of tissues. Now, meanwhile, you have the same volume of blood you had a minute ago, right? Like you don't have any more blood compared to before. So now what's going to happen is your body's going to go, all right, well, we only have limited blood. Let's close down some blood vessels elsewhere. And so the blood vessels going to your digestive system close up a little bit, and your digestive system sort of shuts down in response. And that's why you don't get hungry in the middle of your workout, but you often are starving after you're done. Because like you closed up all those blood vessels. Exercise is often considered an appetite suppressant. So then once you're done exercising, your body's like, all right, well, we don't need all that blood to the muscles anymore. Let's go ahead and constrict those. And then it opens up all the blood vessels back in your digestive system. And all of a sudden you're like, that's right, I didn't have breakfast. Oh, I'm going to kill someone, if you don't eat like me. So that is very much like how that kind of works. That is all autonomic. Luckily, we don't have to think about any of that. All right, so now a lot of that was a review, right? We looked at the neuron, we looked at the types of neurons, we looked at the divisions of the nervous system here. Now let's go ahead and look at one of the other really cool parts of our nervous system here, which are our sensory receptors, right? Like if we're going to understand sensory function, right? If we're going to look at the sensory function, we got to understand our sensory receptors. So this is actually another very vital, important part. Like we're going to talk about these sensory receptors all the time. But what sensory receptors are, they are specialized structures located throughout the body designed to transform environmental stimuli into sensory information for the brain. I'm just going to say for the central nervous system to interpret. Right, so this is basically these really cool special structures running throughout your body that gather information and turn that information into something that someone can understand, right? So really good examples of this that are out there. You've got things like nociceptors. Their job, those are your pain receptors. Nociceptors respond when they, you know, for the most part, they just sit there all day. I'm just kind of like hanging out. And then all of a sudden something hits like a certain threshold and they're like, whoa, that hurts, right? And then they just kick on. That's a nociceptor. And so that's where like so all of a sudden you're like doing something, ouch, you know, your nociceptors slowly kick on. If you've ever grabbed something really, really hot and it like wasn't hot enough to burn you enough to like drop it instantly, but you were like hot, 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 you know, like carrying something to the table. That's your nociceptors being like, hey man, maybe let go. But then like eventually, like if it was really hot, you know, you wouldn't have any control. Your hands would literally just open on their own.
Yeah.
You'd experience like an autonomic reaction. Yeah, what's up, Irene?
Yeah, Brett. So does that also apply to something like, say you were doing something and then you suddenly remember something?
Would that be sensory receptors? I don't think so.
Okay, this is more like physical out your environment around you. Okay.
Mm-hmm. These are like physical structures. You're talking a little bit more about like if you like remember something all of a sudden. That would be something that really does kind of take place in like the brain, which would really be more of like related to like our psychology. I think that there would probably be less. Actually, this is not true. Actually, that's not true. I was going to say there'd probably be less like physical, you know, holdable, like tangible, objective pieces that control things like that. But that's not true. Like our brain, you know, our brain is a series of physical things. So our thoughts and our actions are also physical things. But I would say that would probably just be a random neuron in your brain that all of a sudden lights up because it was like sleeping. It's like, hey, I'm trying to remember the name of that one actor, and then that neuron's sleeping, and then all of a sudden, like, yeah, wakes up. It's like Ryan Gosling, you know. That's often like kind of how that works. So that it would, I would say it is a physical thing, but it would be like a neuron more so than it would be like a receptor. Does that make sense? We've stepped just barely, like we stepped just outside of like, I'm no brain expert, like I'm no psychology expert, like but I would which is, yeah, that's what I would say. Now that being said, I will say this: memory is absolutely tied to these physical things. Like what memory is physical changes in your nervous system. Like that's how we develop memories, right? So when I do a bicep curl for the first time in my life, my brain has to figure out what muscle, like what motor units and what route to take. Like it goes from that neuron to that neuron to that neuron. It tries it out the first time, but then like later I'm doing that bicep curl again, and maybe I'm doing it for a heavier weight. Now my brain goes, oh, well, that route didn't work. I wasn't able to recruit enough strength. And so then it goes that neuron to that neuron to that neuron, right? It tries a different path. So, you know, movement and actions, they are physical changes. Like you are changing your neurons. What determines like what movement or thought something is the order of neurons that it goes in, like what neural pathway it takes. It's just like how when you drive in a different destination to work, like your route was slightly different. That resulted in you maybe arriving at a different time or having a different travel time, you know? Your nervous system's constantly doing stuff like that to get more and more and more efficient so that it can burn as little energy as possible. So nociceptors respond to pain. You also have chemoreceptors. Chemoreceptors are the ones that respond to chemical changes, like your taste buds are chemoreceptors. So when some things taste really salty or taste really sweet, or, you know, slightly bitter, like this coffee, that's like a really, you know, that's an interesting thing. Like certain sensory receptors like light up. You have chemoreceptors. My favorite weird fact that I always bring up whenever I talk about chemoreceptors is I talk about cats because I'm a cat fan. But like cats don't have chemoreceptors for glucose because their digestive system doesn't utilize glucose. Their body doesn't use glucose to produce ATP. Their body only uses amino acids and fats. So when you give a cat glucose, they can't taste it. But to them, it tastes the same as like an aluminum can tastes to you, because you don't have chemoreceptors that sense aluminum, because aluminum is not food to us.
Wow.
Yeah, kind of fun, right? And so you're designed to be able to taste the things that you can, consume for food. Then you got photoreceptors. Photoreceptors respond to light. This is, by the way, I hate to be like a ruiner here, but if you've ever had, I feel like this is a conversation you have at a bar when you're like a few drinks deep. But it's like you have that conversation where you're like, how do I know that like your blue isn't my red? We do know. We can measure it. We can we know that everyone's blue for the most part is the same, unless you are missing some of those cones, or if your nervous system doesn't connect to those cones very effectively, then you might experience something like color blindness. I remember being in school, and we learned about color blindness in, like, I was in high school, and I remember learning about it in my biology class, that I was surely not paying attention in, because I didn't know it was going to be important at any point in my life. But we were all sitting there, and our teacher was explaining like color blindness to us because it was in the textbook, and they showed like a colorblind test, like that circle with like a bunch of dots in different colors, and then like there's a number in the center, and if you aren't colorblind, you can tell the difference. You can see the number 6 in the circle. And we're all sitting there, and we're all goofing around, and then all of a sudden, like, our teacher's like, so if you look in the book, you can see the number 6. And we have a friend of mine named Ben, who's like, what are you guys talking about? There's nothing there. And we were all like, and he found out he had gone, like 16 years of his life without realizing he was colorblind. Because to him, he had learned the different shades of things. And he thought that's just how the world was. And that was the moment Ben Lilly realized he was colorblind. And the next time we went over, like next time we were at his house, we were like, you realize that your chair and your sofa are not the same color. And he was like, what? Yeah, question, what's up?
Yeah, Brad. So speaking of the color blindness, is it usually like the purple and the gray that they have hard time telling apart? I remember hearing something related to that with the color blind.
Maybe. I actually don't know. I'm no expert. I can't remember what colors seem really similar. I know that a lot of people are red-green colorblind. I know that's like a very common one. Those two colors in particular.
And it's more common amongst men than women.
Very much so. Yeah, very true. Yeah. Which I don't know why either. I like to mention these things, but this is where we're outside of my expertise. Your photoreceptors don't lift weights. All right, so for the relevance of this course, we're going to talk about mechanoreceptors. This is the one that's important to us. So mechanoreceptors, they are the mechanical receptors that sense physical changes, right? So these are sensory receptors that sense physical changes, things like touch, pressure, acceleration, stretch, etc. Right? So those are your mechanoreceptors. Did I get this right? Nope. No, it's got it in there. So that's what we spend most of our, that's how our body develops proprioception, is these mechanoreceptors are triggered. So we're going to talk about 3 main categories of mechanoreceptors here. The first one we're going to talk about is what's called a muscle spindle. So this is where, remember I mentioned the neuromuscular system, right? So your muscle spindle is in your muscle. It runs the entire length of your muscle. But really, it's part of your nervous system. It's how your nervous system understands where your muscle is in relation to its overall length. So these are sensory receptors that run through the length of the whole muscle and are sensitive to changes in length and rate of length change. Okay, so that's the it's not gonna work. Length. So their job is to like sense how long a muscle is, right? They are sending signals to the brain saying like, hey, like if I'm in this position here, my biceps all bunched up, right? It's saying, hey brain, the bicep is at 0% max length, right? If I'm like fully just like, I can't bend my elbow anymore, right? Like if I'm just ripping down like this, I'm feeling pain in my elbow right now, but like my bicep is sending a signal to my brain being like, yeah, I can't contract anymore. That's as far as I can go, right? And I'm feeling pain in my elbow because I'm being pulled by another receptor, which is a joint receptor. There's too much pressure in there. Now, if I go the opposite direction, right? If I stretch this out all the way, like let's say I take my arm up here and I just pull back like crazy, I'm gonna start feeling this big stretch in my bicep. And that's where the muscle spindle is starting to activate, saying, hey, 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 brain, 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 we are at 100% length. If you go any further, you're going to tear us in half, right? And that's what a muscle spindle's purpose is. It's basically to tell the brain, whoa, hey, shut it down, right? You can't go any longer. You go any longer, we're going to tear. Now, you also have another sensory receptor called a Golgi tendon organ. Remember earlier I mentioned proprioception? This is how we're getting that proprioception, right? Which is why these three things are also the other most important thing to learn today. So Golgi tendon organs, they are sensory receptors that are located in the tendons of a muscle that are sensitive to changes in tension and rate of tension change. So Golgi tendon organs, they live at like my insertions and my origins of my muscles, right? So they're at the origin and insertion. They're there to tell my brain how much tension there is. They're like, hey, we're about to get ripped off the bone. You should probably relax, right? We're at maximum tension. Again, if I'm stretched like this, where it's all bent, I'm at very little tension, right? Like there's the muscles at very little length, and so it's just holding on very, very easily. But if I stretch out like crazy, maximum length, that means there's also maximum tension. And so the Golgi tendon organ and the muscle spindle, for the most part, they work together. Here's where the problem lies. Sometimes they work together to lie to your brain, particularly this guy right here. The muscle spindle, he is a filthy, filthy liar. And the muscle spindle really loves to tell the brain, hey, we're at max length and we can't stretch any further. You should relax now. Or you should create a pain, you shouldn't relax now. You should create a pain signal now so that the Yahoo in charge decides to stop stretching, right? And that's that stretching sensation that you feel when you start to stretch your muscles out. Like if I, reach down to touch my toe, right? My muscle spindle starts sending a signal to my brain as I reach for my hamstring's being pulled longer and longer and longer and longer. And once it reaches a certain threshold, my muscle spindle starts saying, hey, we can't go any longer. If you go any longer, that's gonna tear us in half. But they love to lie. Like in an overactive muscle, the muscle spindle loves to say, hey, we're at max length, when it's actually not. There's actually way more room for you to stretch. Now, when it does that, when it sends that, hey, we're about to tear signal, it activates the Golgi tendon organ with it. The Golgi tendon organ's like, yeah, I mean, he must be telling the truth, right? Like, I guess that's true. If he's going to tear, then maybe I'm probably going to tear off the bone too. Because there's a connection between the two. Maximum length means oftentimes maximal tension. But what's kind of cool is if you put pressure on a Golgi tendon organ, whether that's by actively putting pressure, by squeezing, or by stretching it end to end and sitting in that kind of discomfort, when you put pressure on a Golgi tendon organ, it freaks out along with the muscle spindle for a little while. So it's like, wah, 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 wah. Like, we gotta stop, we gotta stop, we gotta stop. And so you're feeling this like, deep stretch. You're like, oh God, right? That's what you're kind of feeling there. That's your muscle spindle and Golgi tendon organ freaking out, telling the brain like, hey, back off, you should stop. And then, it's telling you to go back to a resting position. But what's interesting is if you put pressure on a Golgi tendon organ for about 30 seconds or so, if you hold it for long enough, the Golgi tendon organ starts to realize there's very little tension actually. So it's like, wah, 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 wah. this is not that dangerous. And so then it actually inhibits the muscle spindle. It says, muscle spindle, you're being a real drama queen, shut it down. And it actually inhibits it. This is how we as trainers use stretching to improve our clients' range of motion. So if I've got like rounded shoulders, right? I've got a muscle spindle running through my pectoralis major, which is in charge of, rounding my shoulders, that is overactive. It's basically lying to the brain saying, no, we can't stretch any further. You got to stay in this bunched up position. And it says it all day long. But if I do a stretch, right? If I go like this and I stretch away, it's tender. It's like, and it starts freaking out. But if I hold it long enough for about 30 seconds, what's going to happen is the muscle spindle, which is located here at the origin, and maybe at the insertion, but usually it's this one here, that Golgi tendon organ starts to realize there's actually very little tension, and I should be at a bigger range of motion because the muscle has plenty of room to relax. So then it will inhibit the muscle spindle, and all of a sudden, after about 30 seconds time, I'll get all this extra range of motion and I'll stretch further. And that's how static stretches, those big long duration 30-second stretches, that's how that actually works. That's how we are using this physiologic process in order to make that occur. Does that make sense, Raul?
Yeah, a little bit.
Yeah, I mean, it's going to come around again plenty of times. We're going to talk about this concept a lot. Every time we talk about flexibility, we're going to revisit this. So it'll get clearer and clearer. But yeah, that's kind of how that communication sort of works. And we have a name for that we'll get to in later classes. Now, the last receptor that we've got are also our joint receptors. There's a kind of a grouping of these. There's one that like there are all these like fun different names that are in there. But your joint receptors, their job is to these are sensory receptors that respond to pressure, acceleration, deceleration of joints. So again, that's also how your body's understanding where it is in space. If there's a lot of pressure here, this is at a certain length, and this is at a certain tension, my body knows that my arm is here. But if all those numbers change, then it knows that it's here and here and here. And that's how I have proprioception. Thanks to all these fun receptors here, sending info to the brain. So what's cool about this is when it comes to like exercising, your clients and you get better at stuff pretty quickly in the beginning. I love it when I've got like a real newbie in the gym who's really never exercised before. And they start exercising for the first time in their life. And all of a sudden, all their numbers just go up. They're like, that was way easier today than the last session. That's like, yeah, like, I'm really getting stronger. And they're objectively, they are getting stronger, but it's not because their muscles are getting larger. It's because your nervous system is getting better at controlling the body. So early stage improvements when it comes to physical activity are largely due to changes in your nervous system, more so than it's changes in like your body experiencing muscle growth. But it's funny, your clients will totally convince themselves. They're like, I can see some definition in the mirror. And it's like, you've been working out for 1 week. I mean, I would, for the record, I've never once corrected somebody. I just go, okay, cool. Because they should be allowed to live in that awesome fantasy. But yeah, that's kind of what we see there. Any questions about the nervous system before we move to the old skeletal system here?
No, I think we're all right.
Alrighty. All right, so now I'm on the, I'm trying to make sure that I'm like lined up properly here. By the way, you've never seen me in like real class, but Irene, if you've ever wondered why I'm so strict about how I do my indentations on the whiteboard, it's because of documents like this.
I love it. It keeps things so organized. Thank you for that.
I friggin' hope so, man, because I was like, that was the one thing I was actually somewhat good at like in school, is I was like really organized about how I did my notes. But no one could ever read them because of my bad handwriting.
It shapes the like taking notes, like it's like the brick. You're starting with the bricks, having the basic down, the way you organize it.
It's like this
Thumbs up.
falls under this.
Yes, I love it. Thank you.
Cool. All right, so our skeletal system, right? This is the second part of our kinetic chain, at least second part for us today. So the skeletal system, right, is the framework and structure of the body by which we manipulate to produce movement. So your skeletal system is how we actually, it's what we have in order to be able to manipulate. So it provides a resting ground for our muscles, but also because the skeletal system is comprised of joints, it's how our muscles are able to bend certain segments and create movement, right? So that is going to consist of, bones, joints, and connective tissue, right? So our divisions here, you're going to have your axial skeleton, that's your skull, your rib cage, and your vertebrae, like all your vertebrae running down all the way to the bottom at your coccyx. And then you've got your appendicular skeleton, which is your appendages. That's your arms, that's your upper appendicular, and your legs, that's your lower appendicular. Both of those are held on with girdles. You have your pelvic girdle, which is your hip bones, and you've got your shoulder girdle, which is your scapula working together with your collarbone. So those are the two like girdles that kind of hold everything on there. So your bones, right, and I should probably, let's see here, we'll put the bones first, right, bones act as levers for the muscular system to manipulate. And we'll get joints down in just a little bit, and then we'll get connective tissue down there in joints probably. So your bones constantly go through like what's called bone remodeling, which is the constant breaking down and growth of bone tissue. So the two cells that are responsible for our bone remodeling are going to be those osteoclasts, right? Which are specialized, oh my God, typing, cells responsible for breaking down old or damaged bone tissue. And you've got your osteoblasts, which are specialized cells responsible for building up new bone tissue. Right, so your osteoclasts come along and kind of eat up any imperfections in your bone, and then osteoblasts come along and lay down new ones that make them much more like sturdy and stable. And that's how we increase bone density. We know that exercise increases bone density. Whenever you're doing like heavy barbell squats, for instance, that's a weight-bearing exercise. Weight-bearing exercise in particular has been shown to improve bone density better than any other type of exercise. And when I say weight-bearing, what I mean is exercise that works against gravity in particular. I love swimming, I love cycling, I love resistance bands. I think all those things are great, but they are not considered weight-bearing exercise because they're using like tension or like viscosity, in order to like apply a resistance. And there is something special about gravity in particular that really generates bone tissue and bone density. So by, squatting against gravity, and you can enhance that gravity by putting a weight on your back, that is what's been shown to like improve bone density. Running improves bone density more so than like cycling does because it's working against gravity more so than it's working against like tension. And that's also probably due to the fact that like it's also kind of high impact. It's also why running is so kind of hard on us sometimes. If you don't have proper nutrition and proper sleep and you do a lot of running, you might experience like a running injury because you're overtraining because, it is high impact. It is like lots of pounding. This is where things like, if you've ever seen the Power Plate, they'll sell at Costco sometimes, which is weird, but like Power Plate is a company that makes this little plate that you stand, it's like, it's about this big, it's like a platform and you stand on it and it's got handles if you need them, but you're supposed to like work out on the Power Plate. So you do squats and stuff and the Power Plate just goes boom and it just vibrates like crazy at a super, super, super high frequency. And that frequency creates like, you're basically just like punching and slowly like breaking away bone tissue. And so then your body goes, holy crap, I need bone tissue. And so your osteoblasts become really, really active. And so like they'll put people who are like cancer survivors or people with osteoporosis, they'll oftentimes recommend using like power plates to kind of get them back to neutral. They kind of look like this actually, power plate. That's actually not it. That's a, whoa, $15, no. Oh, it's a trial for the program if you want to buy, if you already have one. I was like, no way. So yeah, it's this little thing that kind of looks like this. Yeah, $13,000. That sounds about right.
They feel so awesome.
Yeah, they're really cool. They really are like pretty unique. I'm just gonna mention one more cat thing that's kind of fun here, but like they think this is why cats' bones heal so fast compared to like other animals.
Oh, yes, I remember you talking.
The purring, yeah, they think like the purring is at a frequency similar to like what causes bone growth.
Wow.
They've looked at like applying that to humans. Like they've looked at like putting people in casts that have like batteries and then they just like vibrate with the idea of like building their bone tissue up faster. So far, I don't think the results have been conclusive, but I'm pretty sure like they've done some interesting
Awesome fun fact.
stuff. Yeah, right. That's also why cats actually, they don't just purr when they're happy, they purr when they're hurt. But types of bones you've got long bones, which are long in nature. They're usually, kind of cylindrical. Then you got short bones. These are sometimes known as cuboid bones or flat bones. I'm sorry, well, sorry, not flat bones, but cuboid bones. These are your short bones, right? They usually like comprise like gliding joints and things like that. Your wrist, your ankle, they're really good classic examples of short bones. You got flat bones, which are really thin and protective, like your pelvis, for instance, or your scapula. And then you've got irregular bones, which are just really weird in shape, right? Like your spine's a classic example of that. You got all these kind of interesting facet joints and stuff. Now, in your bones, you're also going to have special bone markings. Actually, I guess I'll hold on really quick. We'll go types of bones. Now you got long bones. Actually, you know what? We'll do this. Bones. Long, short, flat, irregular. Those are the sort of like most common ones. Now you do also have like specialized bone markings on there as well. Bone markings are what allow muscles to have a place to grip, right? So you're gonna see like flattened or indented portions of bones that allow muscles to have a good site for allow muscles to have a good grip. Actually, that's a great way to put it. So this is what allows like your muscles to actually attach, right? Two of the most common ones that are depressions are going to be things like fossas and sulcuses, which are basically like these little like indentations. If you ever look at like, this is called the spine of your scapula. If you ever look at like the spine, you'll notice it has this kind of like indentation running along it. And that's what allows muscles to attach to. You've also got processes, right? So like processes are little projections that run out from your bones. If you look here, oops, hold on. If you look like here, right, we've got like little processes and things like that, little processes that allow muscles to have something to attach to. So condyles, epicondyles, tubercles, trochanters, things like that. Like the most common one that you're gonna see a lot is like, we talk about all the time is your greater trochanter of the femur. And it's this big knob right here, right? So this is the head of your femur, but this is your greater trochanter right here. And what that is that's actually where your TFL attaches. So this little muscle that runs in your hip from the top over here and inserts. It's also where your gluteus medius inserts as well. So if you've ever had like a burning sensation in your hip, or if you've ever had runner's knee, a lot of times that's because where this muscle that runs down from here all the way down to here gets really tight and it starts to rub on that greater trochanter. So if we need to, oh, actually, there's a great picture. So if we need this muscle, oh, that's the gluteus medius actually. TFL would probably be like right over here. But if you see it like running like from here to here, we need to be able to place a foam roller basically between this bony point, which is the bony point like up here on like the top of your hip. And then we need to place it between where your greater trochanter, which is that knob, you know, down the femur off to the side. And so if you place a foam roller right here, we're going to try to get that muscle to relax. That's a pretty common one that we talk about a lot. So those are some of your bone markings. You've also got your vertebral column. You're going to have different sections here, right? You're going to have your cervical vertebrae, which is your neck, your thoracic vertebrae, which is your upper back, your lumbar vertebrae, which is your lower back, and then at the very bottom, you are going to have your sacrum and your coccyx. That's your tailbone there. So those are things that we see in the bones. Now, the next section we got to talk about are your joints, right? Whoops. Joints are the structures where two or more bones articulate with, I said two or more? One or more bones. One or more bones articulates with another, right? So joints are where two bones come together, basically, right? And so joint motion, we're going to refer to that as arthrokinematics, which is like one of my favorite dumb examples of a term. Arthrokinematics, which stands for joint motion, which is literally, the definition is less letters than the word. Why do we even have that word? But that's what arthrokinematics is. I've been complaining about that since I went to school. So your three types of arthrokinematics that we're going to see are going to be rolling action, right, which is where one joint rolls over another, right? We're going to see a sliding action, which is where one joint surface, joint surface slides over another, right? The carpals of your wrist are an example of that. Like when I move my wrist around, they kind of, you know, they're both like flat bones, and they kind of, I'm sorry, they're both short bones, and so they make this kind of sliding action. And then we got spinning, right? And spinning action is where one joint surface rotates around another one. So spinning action is what you see in like your forearm, right? When you spin, there's one bone that's literally spinning just like that. So those are kind of the three main arthrokinematics that we see. And then what we're going to do is we're going to classify our joints into two major categories here. So two major categories, which are going to be non-synovial joints. I'm going to put those first because we don't have much to talk about. Non-synovial joints, which are joints with no joint cavity and are either non-movable or only slightly movable. So there's technically two categories within that, but we can just call those like they're either fibrous joints or they are cartilaginous joints. Either way, they're really not movable. Technically, cartilaginous joints are semi-movable, but we don't need three categories. So then we got synovial joints. Synovial joints are fully movable joints, right? They have a joint cavity, which provides more space and allows for a greater range of motion. They also produce synovial fluid and often have specialized other structures to eliminate friction and provide stability. So in your non-synovial joints, you're often going to see that they have like a joint cavity. There's a lot of space in there, right? And women are going to have more space in their joints than men are in certain cases. And that's why women tend to be like more flexible than men in a lot of different areas, right? There's actually more space there. And so we're going to see that very, very, very commonly. Unfortunately, one of the issues with that is it also often leads to women developing rheumatoid arthritis much more commonly than men because of that extra space. There's just room for your autoimmune system to kind of eat away. Doesn't mean it's going to happen for sure. It just means we typically see that more commonly in those populations. So greater space, greater range of motion. Greater range of motion means decreased stability, which means you're more likely to dislocate a joint. And that's why we have all these other specialized structures that are there to provide stability, right? So your joints provide the bones the ability to be manipulated, right? It allows them to kind of change positions. And so what we need to understand about like joints is that like movement of one joint will directly affect the movement of another one. One of the most common things that we're going to talk about in later classes is we're going to look at certain types of posture, and we're going to look at something called pronation distortion syndrome. And pronation distortion syndrome is when you notice somebody who has posture where their feet ever so slightly turn out, their feet flatten down towards the ground and sit like this, and then that actually causes their knees to internally rotate and adduct towards our center, right? So if I stand neutral, this is what I should be looking like. But if I have pronation distortion syndrome, a lot of times like I'll be standing with posture like this. So that's distortion, right? That's a joint sitting in an angle that it really shouldn't be. And so because of that, it causes friction and it causes muscles to be recruited the wrong way, and it causes aches and pains. So we need to know what muscles cause that pronation so that we can stretch those muscles out. And we need to understand what muscles strengthen us into supination in order to like pull them back to neutral. And that's really where like the industry of personal training kind of came from. So those are our two main categories of joints here. And then the last thing that we've got in our skeletal system is going to be our joint. So we've got our bones, we got our joints, and we've got our connective tissue. So joint connective tissue, right? So this is going to be the tissues that provide stability and hold two or more bones together, right? So our joint connective tissue are going to be, the classic example are things like ligaments, right? Ligaments are going to be special structures that attach one bone to another, right? So that's what a ligament is. It's there to connect bone to bone. I love and hate this picture simultaneously because this is the picture that's in your textbook. I love it because it does show ligaments, right? There's one right there. That is your MCL ligament. That's your medial collateral ligament. But I also hate this picture because you can see there's a tendon and they are very similar looking, and it often leads to students getting confused. So don't get confused. Ligaments attach bones to bones. Tendons attach muscles to bones. Things that we need to know about ligaments: they are characterized by poor vascularity, meaning they do not receive adequate blood flow. So because of that, they repair much more slowly. They repair and adapt much more slowly than high blood flow tissues. So that's one thing about your ligaments that we need to remember. Your ligaments are what repair kind of slowly. So one of the reasons why it's so important to take rest days when it comes to exercising is because those rest days are going to ensure that your ligaments do not get overworked and eventually tear and disconnect your bone. So weight-bearing exercises, like I mentioned, I forgot this is actually in this PowerPoint. Weight-bearing exercises are exercises that force the body to work against gravity. Running, lifting weights, body weight exercises like calisthenics, all of those are weight-bearing, and they are very good for your skeletal system. Swimming and cycling are not, because they are working, in swimming it's working against like the viscosity, and cycling it's working against like friction, you know? Both those things are great, by the way. Like these are great ways to develop your body. But if you have bone density issues, they're probably not our first choice. So we want to help and build our maintain our bones, our connective tissue, and the benefit is that they also burn lots of calories. All right, any questions before we move on to the muscular system? Yeah, what's up?
I so appreciate the distinction between the tendon and the ligament, because I was gonna ask that because they're kind of similar. Yeah.
I know, it drives me crazy. And what's funny is the same picture show up later. When we talk about tendons, you're gonna see that picture.
So so tendon always attaches from muscle to bone, vice versa, and ligament is always bone to bone.
Yep. So here, muscle anatomy, Golgi tendon organ, and muscle spindle. I want to make sure I get a picture that has all of it. Close, really, really close. Yeah, there we go, that'll work. Okay, so see this picture right here? It doesn't have the whole, I would love it if it had like a picture of a whole muscle, but like here's the muscle belly, right? And then if you see on the inside of the muscle belly, see these little things wrapping around it? They're like a coil, right? So when the coils are bunched up, that's the muscle spindle realizing there's very little length. And when the coils are kind of pulled apart, that's where the muscle spindle realizes they're pulled at a lot of length. So that's where the muscle spindle is located. It runs throughout the entire fibers here, and it's telling your brain how long your muscle is. Meanwhile, at your joint, at your tendon, right? And so you see your muscle becomes a tendon at the end, and it would insert onto a bone down here at the bottom. That's where your Golgi tendon organ is located. And that's why when we're foam rolling, we never want to like place a foam roller on a bony point, but we do want to put our pressure somewhat near the insertions or the origins. So like, I don't want to place the foam roller on my bone because that can cause bruising, but I do want to move just slightly off the bone so that I can put pressure on the tendon. And that's where I apply pressure to a Golgi tendon organ, which inhibits the muscle spindle. Does that make sense? Oh, and there's what they look like when they're all stretched out or relaxed. That's kind of nice. So yeah, there we go. That's actually the picture I was kind of looking for. All your muscles end in a tendon on both sides, and then it grabs the bone. Okay, let's get back to the muscles, shall we? Let's do the muscular system. The white one? Yeah. One more. There we go. So the muscular system, right, is a series of muscles that generate internal tension in order to overcome external forces, right? So your muscular system's in charge of like generating your posture. It sometimes generates heat, but it manipulates your bones, right? In order to overcome external forces. I'm actually gonna say by manipulating the skeletal system. And I'm actually gonna change this also slightly. A series of muscles under the control of the nervous system that generate internal tension in order to overcome external forces, and they do it by manipulating the skeletal system. So we've kind of built the whole kinetic chain here, right? Your muscles are controlled by your nervous system, and then your muscles move your skeletal system, and that's really their main job, right? So what a muscle is, by definition, a muscle is a compilation. What have I done? Oh my God. Did I hit a shortcut somehow and turn the font onto all caps? I did. I don't know how I did that. I was like hitting the caps lock key and it wasn't having any effect. A compilation of many individual muscle fibers or cells that are neatly wrapped together with connective tissue to form bundles. Okay, so that's like what a muscle is. It's a whole bunch of muscle fibers, a whole bunch of muscle cells coming together. And this is why each of your muscles are considered technically their own individual organ every time. So the first layer, and really quickly we'll mention like what a muscle fiber is, right? A muscle fiber is an individual muscle cell filled with contractile proteins. And those contractile proteins are the actin and myosin that we mentioned earlier, right? So that's what a muscle fiber is. And so a muscle is a bundle of a bundle of a bundle of a bundle, right? And there's that freaking picture again when we get to connective tissue. So in a muscle, you're going to see things like fascicles, right? A fascicle is a bundle of individual muscle fibers wrapped together. Let me just say that, actually. I already said the word bundle. So, so a muscle fiber is the individual cell. And if you wrap a bunch of cells together, you get a fascicle. And if you wrap a bunch of fascicles together and wrap them all up, you get a muscle, right? And then each muscle is going to end in a tendon, right? So then your tendon is connective tissue that attaches muscles to bones. This is another classic example. This is also one thing that I kind of hate about this picture. See this picture here? You can see this section here is a really accurate representation of like how a tendon works, right? Like the muscle runs along and kind of grabs this whole section of bone here. This here, where it comes in and attaches to the top of your patella, and then there's another bit that attaches to your bottom of your patella. The way this is drawn, it kind of looks as if this tendon inserts, then picks up, like makes another tendon, then inserts down here. That's actually not how this works. Your quadriceps tendon runs over top of your patella. It runs over top of your kneecap, uninterrupted. So I don't know. They didn't draw. I guess they couldn't show it with shading or whatever. But if we look at the quadriceps tendon, there we go. This is a much better picture. You can kind of see it actually wraps over top of it like that, not grabbing here and then picking up down here. Because that's not how that wouldn't work that way, right? Like we wouldn't have any muscle by which for this tendon to really do much, right? So that's really what we're kind of seeing there. So if you're looking at that, right, we call that your patellar tendon. Again, remember Golgi tendon organs, they live in the tendon. This right here is where your doctor is going to try and smack you when they do that knee test. When they do that reflex test, they try to kick you right here. And what that does is, remember earlier how I mentioned Golgi tendon organs, their job is to sense tension. If there's a lot of tension, the Golgi tendon organ wants to protect the muscle. The muscle is protected if it's not super stretched out. So when you hit it really hard right here, that creates a stretch reflex, which means that your brain you kind of fooled your brain into thinking that you just bent your knee like really hard and really fast. So then your nervous system autonomically decided to go, whoa, shorten that muscle. And so it contracted the quadricep in order to reduce its length, and that's what kicks the leg forward. Does that make sense?
Yeah.
Cool. We use stretch reflexes all the time. It's one of the best tools that we have in our toolbox to actually make somebody jump higher. But we'll look at that later. So again, tendons, just like ligaments, and this is why they're often mixed up, are characterized by poor vascularity. Right? They don't get as much blood flow, and so they are susceptible to slower adaptation and slower repair. Right? So they do, they get beat up just as easily as the muscles do, but they don't repair very quickly. All right, so now we're back to kind of looking at our muscle fibers again. Right? We're seeing all this series of terms here. So if we look at our muscle fibers, a typical muscle cell, when you zoom in on it like crazy, you're going to see a couple like specialized structures in here. You're going to see remember we mentioned cytoplasm, right? That's the fluid within a muscle cell. That's the fluid within a cell. We give muscle cells a special name. We're going to call it sarcoplasm. Sarco means sarc means flesh, I think, or maybe sarco means flesh. But that's where we're getting like, this is where whenever you hear the word sarco, we're in muscle territory. You're talking about muscles. So sarcoplasm is the fluid portion of a muscle cell. And it's special because it has glycogen in it. It's got some fats in there. It has special minerals that are related, like electrolytes and things like that. But it's also got myoglobin, which is a protein that carries oxygen molecules, and it is special. Myo is another term that means muscle. And myoglobin is special to muscle cells. Whereas like you have hemoglobin in your blood cells to carry oxygen, myoglobin carries oxygen in your muscle cells. So we got two special terms there, but they're very similar to like other terms that we already knew, right? Cytoplasm, we have sarcoplasm in muscles. Hemoglobin, we have myoglobin in muscles. Then you're going to see a nucleus, then you're going to see mitochondria, all the normal stuff that we normally see. But one thing that's totally special is that they have myofibrils or myofibrils, which are those myofilaments that I mentioned, right? That's the sarcomere that you can see here. Muscle fiber components, right? Let's go ahead and look at those individual bits there. So again, if a muscle fiber is an individual cell, it's going to have special components inside of it. So you're going to see what are called myofibrils, which are special sections of a muscle fiber that contain myofilaments such as actin and myosin. Right? So that's what a myofibril is. So the area in which they live is called the sarcomere. So sarcomere, right, is going to be the functional unit of the muscular system. It is the area in which myofilaments overlap each other. Okay? So this is like, the myofibrils are like, this whole like filament section here. And then the myofilaments that we're talking about are actin and myosin. So actin is, again, just like yesterday, the thin filaments that has binding sites for myosin to bind to. So actin's the thin filament here. And then you've got myosin, which is the thick filament. The thick filament, which binds to actin. Okay. Actually, we'll say thick filament with heads that bind to actin. So then you also, I should say, we have the regulatory proteins. Troponin and tropomyosin are regulatory proteins that live on actin to block its binding sites during a muscle's relaxation. Okay, so troponin and tropomyosin are there to block things when we want to make sure that your muscle is relaxed. But actin wants to bind, or myosin wants to bind to actin all of the time. So you can see that actually here, right? One other term that I'm going to put here is also, I'm going to put a Z line. This is a term that we haven't really used that often yet, but a Z line is the area between two sarcomeres that
I think you talked about it last time.
Yeah, I think I mentioned it, but I didn't put it in the notes. So the Z line is the area between two sarcomeres denoted by a zigzag pattern. And then when a muscle fiber contracts, it is pulling the two Z lines closer towards each other. So that's like what's happening, right? When this Z line right here, which they totally didn't draw in a Z, but this Z line is going to move in this direction. This Z line is going to move in that direction. So the sarcomere is going to shorten. Meanwhile, that's happening in this other Z line right over here as well. Those are your contractile elements, and that's what we're seeing inside of a muscle fiber, right? So those two proteins that are also really important, right? We got troponin and tropomyosin there. They are there to block those binding sites in relaxation. Tropomyosin's actually like a big long string, and troponin is the one that actually has like a binding site that binds to calcium, and troponin's attached to tropomyosin. So when troponin moves, it pulls the string with it. And that's how it gets out of the way. So when we look at like generating force within a muscle, right, we do know that's under the control of your nervous system. So here's one of your spinal discs, right? And what'll happen is you're going to experience a simultaneous contraction. Remember how later on in this lesson and later on when we were talking about muscles, we talked about Batman, Robin, and the Joker, right? We talked about agonists and antagonists, right?
Yeah.
One muscle is pulling while the other muscle is lengthening. Those are concentric and eccentric contractions, right? So when you get neural activation, your nervous system is going to send two signals simultaneously. It is going to send a signal to this muscle, which causes it to contract, and it's going to send a signal to this antagonist muscle, which causes it to relax. Okay, so your nervous system is designed to tell Batman to start doing work and tell the Joker to relax. It tells Batman to work concentrically. It tells the Joker to work eccentrically. Does that make sense?
Yeah.
And I'm moving a little quick, but so that's those the two types of like contractions that we're seeing simultaneously. Now, that's what's supposed to happen, but it doesn't always happen that way. And that's where, remember earlier I was talking about poor posture, right? If you say, hey, you're supposed to contract, and then the nervous system says, hey, you're supposed to relax, and then this muscle goes, okay, I'm going to contract, but then this muscle says, well, I don't want to relax. I also want to contract. And they both contract simultaneously. You lose force. And that is how we end up with altered posture. I've got a muscle here that's pulling harder than it's supposed to, and I've got muscles back here that can't pull as much as they're supposed to because this one won't turn off. That is what we call an overactive muscle versus an underactive muscle, at least in this case, right? And it could go in both directions, but I've never seen somebody with like overactive upper back muscles. That just does not happen. We live in a world with cell phones. So that's where we understand like our overactive, underactive thing. Now, what's kind of cool about this, remember earlier we talked about like putting pressure on a Golgi tendon organ? That makes the muscle spindle relax, and that allows me to get my posture back, right? That relaxes that muscle. Now I can actually do that in that version. That's a big, long, slow stretch, right? What do we call that? A static stretch. So where I hold it for about 30 seconds, that gives the Golgi tendon organ time to shut down the muscle spindle. And that's why we traditionally hold all of our stretches for 30 seconds. At least that's what most people think. But we as trainers have other types of stretches. You know, we've got arm circles. We've got things that are not these big, long holds, right? So a lot of people kind of only know about static stretches, but there's another category that we call active isolated stretches. And active stretches are actually where you do the same movement, right? So, but rather than holding like this for 30 seconds, what I'm going to do is I'm actually going to contract my upper back and try to relax my chest and pull myself in, hold for about 2 seconds, and then relax. Then I'm going to contract my upper back again. Then I'm going to contract my upper back again. And what I'm doing is I'm trying to get this right here, this neural activation, I'm trying to get it to kick in. I'm actually trying to say like, hey, Batman, do your job. Hey, Joker, relax. Do your job. Relax, right? Over and over and over. And eventually it's going to get through. And that's what we do. We have numbers that we use for that. We hold our stretches for about 1 to 2 seconds. And we do anywhere from like 8 to 10 repetitions. And hopefully that's enough repetitions to get one muscle turned on and the other muscle turned off. Those are called active isolated stretches. And we'll use those in later, like when we get to our program design classes, we'll come back to this concept. So let me go back here and yeah, what's up, Irene?
Can you please re-explain characterized by poor vascularity for tendon?
Yeah, so they just don't get as much blood flow. There's just not as many like blood vessels that you get a lot of blood vessels in. That's actually why their colors are drawn differently. See how like your muscles are bright red? That's because they get like a lot of blood flow. And then like your tendons are usually drawn as kind of white and like poorly colored. Those are your like poor blood flow areas. They just don't get as much blood flow, and because of that, they don't repair very easily. They don't get, like, blood flow isn't just how we deliver oxygen, it's how we also deliver like nutrients and repairing, you know, amino acids and things like that. So
Got it.
if you can't do that, they can't repair it quite as quickly.
Is that how like amino acids help you build your muscles bigger because you're adding more?
Yeah, basically. Yeah, you're reassembling them. Your immune system comes along, uses these special immune cells. They're called cytokines. And cytokines trigger, like, they're like, all right, well, we're going to lay down more amino acids. Like, this keeps getting torn down at its current size, so we're going to make it a little bit bigger and hope that it doesn't get torn down anymore.
What are good supplements to take? Do you take anything?
Not really. I'm not very pro supplement. The big one that I am a proponent of is just regular old whey protein. It's a very easily digestible protein, so your body's able to break it into amino acids really quickly. But the research as to whether like BCAA supplements and drinks, the research around like whether or not that actually builds your muscles up faster is pretty shaky. Like a lot of times people are like theoretically it makes sense, right? They're amino acids that are important for muscle production. So eating more of them should result in more muscle production.
Yeah.
Theoretically, that sounds really good. But when you actually do it, it's like, well, yeah, if you're not getting enough amino acids in your diet, of course it's going to make a difference. But if you have plenty of protein in your diet, it hasn't really been proven to actually help.
Okay.
You might get a little like benefit out of it. I'm not saying it's impossible, but I am saying it's expensive and the benefits are tiny. So the three supplements that like I'm a firm believer in, regular old whey protein, caffeine, although I don't think it's necessary, I think it is proven that caffeine works.
I drink, it helps muscle growth, coffee.
Oh yeah, I've seen that stuff. I've never tried it. Is it good?
Wait, no, I was asking, coffee helps muscle growth?
Oh, I'm sorry. I thought you were talking about this. There's this anabolic coffee. That's what they call it, anabolic coffee. You'll see this. Where the heck is it? Yeah, this stuff like right here. Or is it this stuff? Whatever. Anyway, there's companies out there that sell like coffee with protein in it. Caffeine is actually more what I'm talking about. Not just coffee, but caffeine, it's not necessarily that it makes your muscles grow larger, but it does enhance your performance. So it's a supplement that has been proven to like give you, allow you to produce energy more effectively so then you can work a little harder.
Yeah.
And working harder is key to muscle growth. So it's not that caffeine makes your muscles grow, it's just that it makes you work hard. And that's been measurable and proven. I'm not saying you need it, but like it's on the list of things that are definitely provable. And then the last one is creatine. Creatine is a supplement that has in every trial shown to, if you're a receptor, if you're a responder at least, some people don't respond. But in every trial with responders, it results in larger muscle growth and it results in greater strength gains because it drives more water into your muscles. And so it causes them to be a little inflated, which then your immune system goes, all right, I guess we'll keep them big. And then also having more creatine allows your body to produce ATP in this very specific way.
Yeah.
So those are the three that I believe in. I'm not like, fish oil pills I think are great. a multivitamin can be helpful. BCAAs, if you're low on protein, I think they can be super helpful. Pre-workout, I think, can give you lots of energy, but I think that's just because of all the stimulants. So I don't think it's any different than caffeine, although it can be more effective than caffeine if it's intense. But you know, if you start getting into like the more like fringe supplements, like, you know, CLA and ZMA and all these different things, the evidence is shaky, you know?
Yeah. Okay.
Okay, so neural activation, right, is going to describe how the nervous system recruits the muscular system, right? And that's where we talk about like motor units, right? So a motor unit is a single motor neuron, right, from before what we were talking about, and all of the muscle fibers it innervates. So you'll notice, like, remember earlier when we were drawing a motor neuron, you know, it's got its big axon there, but then at the very end of the axon, it splits off into all these different things. And so it recruits this muscle fiber and that one and that one and that one. And the more motor units that you recruit, the broader your movement is going to be, you know, like a big, powerful contraction. And the less motor units you recruit, the weaker the contraction. So that's big motor units control big movements, and small ones control small ones. And here is that whole frickin' description from the other day. An electric impulse travels down the central nervous system that ends at an axon. It releases the neurotransmitter into the muscle, into the synaptic cleft, so that neurotransmitter can trigger the muscle. That neurotransmitter is going to be acetylcholine. So that acetylcholine works its way across, binds to the muscle cell. The muscle cell then generates electricity, and that electricity triggers a contraction in the muscle fiber. And so then that muscle fiber, you know, takes it creates the sliding filament action, right? Where all of a sudden, when electricity runs across it, calcium is released. Calcium moves troponin and tropomyosin out of the way. Actin gets bound to by myosin, and it creates the contraction. Phew. And there's the whole freaking thing from start to finish. So I'm gonna go ahead and move past that. All right, let's go ahead and look at our muscle fiber types. So this is what's kind of cool. You do have some different muscle fibers, right? So we have different types of muscle fibers. Okay, so you are going to have what are called type 1 muscle fibers. These are your slow twitch muscle fibers. Okay, so type 1 fibers are muscles that, and by the way, like in terms of like the cells, they just look slightly different. They're still comprised of all the same things. Like the ingredients that make up a muscle fiber, they're identical, right? But they look ever so slightly different when we look. It's like, oh, that one has more mitochondria than that one. Then we're going to say that one's type 1, and we're going to say that one's type 2. It's like the different, you know, they're both birds, but they got different feathers, you know, different colored feathers. So type 1 fibers have more capillaries, more mitochondria, and more myoglobin. Okay, so that's one of the things we're going to see that makes type 1 fibers unique from type 2. They have more blood flow, therefore they get more oxygen. Since they have more oxygen, they have more mitochondria. They are going to be smaller in size. They produce less force, but they are slow to fatigue. Okay, these are your stabilization or endurance type fibers. That's what we mean when we say type 1. Your calves are a classic example of like a type 1 fiber. They can do like slow twitch contractions all day. Then you get type 2 fibers. Right? These are your fast twitch muscle fibers. And these are going to be, these have less capillaries, less mitochondria, and less myoglobin, but they are much larger in size. So they have more sarcoplasm, right? They have more cellular fluid. They produce much more force because because of how much larger they are. They are quick to fatigue compared to slow twitch fibers, and they are used for short-term or force and power type fibers, right? So these are your like explosive fibers. These are the ones that we typically use when we're strength training. These are the ones that we typically use when we are doing cardio. Now, one other thing is that type 2 fibers will, and they're not mentioning it here, but they will be split into 2 subcategories. You've got type 2A fibers, which is your fast twitch, high oxidative fibers. They are semi-slow twitch in that they get more oxygen delivery. So they're still a fast twitch fiber, make no mistake, but they're kind of like a stopgap in between the two. And then you've got your type 2X, which are your true fast twitch fibers. These are your fast twitch glycolytic fibers. And they are true fast twitch fibers used for super explosive heavy type movements. Okay, so those are like the real, like, you know, heavy duty fibers. Those are your fast twitch. So like this might be the difference. Like type 2A might be like a bodybuilder. You know, they do like relatively low reps, but they're still lifting pretty heavy. Whereas type 2X is like a power lifter who's lifting like, you know, 3 reps at the most, you know, but oftentimes it's like 1 done, you know, because that's how they kind of fatigue. These are your different fiber arrangements. This is something you're never going to see really again. But like you got like fan-shaped muscles. It's like your pec, right? Kind of looks like a fan. You have got like longitudinal muscles, which are just big long ones. Your sartorius, it's this big like one that runs down your hips, the longest muscle in your body. You're not going to see these terms again, but all right, lastly, we got to go over muscles as movers again here real quick. And so I'm just going to go back, knock these out. So muscles as movers is the same thing that we did see yesterday. Muscles as movers, right? You're going to see an agonist. That is the main muscle that acts as a prime mover. You're going to see a synergist, which assist prime movers. You're going to have antagonists, which are work opposite prime movers. And then you are going to have stabilizers, which stabilize the body, while agonists are working, right? So they're there to like stabilize everything and keep the body in order. So Batman, Robin, the Joker, Alfred the Butler. All right. So last little bit that we've got here, we got to mention our endocrine system, which is not part of the kinetic chain. So we are actually going all the way back to the first line because this is not officially part of the human movement system. It's a control system. So the endocrine system, I swear NASM couldn't figure out where to put this in the textbook. They were like, we don't want to make a whole chapter out of it. So they just threw it out at the end. But it is a system that consists of a series of glands that secrete hormones to control bodily functions, right? Basically, they have these really cool things that like, trigger reactions throughout the body. So your pituitary gland's the main one. So here's your hypothalamus right here at the very bottom, and your pituitary gland is going to be located right there next to it. And so the pituitary gland has these different lobes that create like different types of hormones. Those hormones trigger other hormones, and then those hormones actually might trigger even more hormones, or they might affect body tissues. So you might create like a hormone that triggers the release of insulin, and then insulin pulls sugar out of your blood. You might trigger the release of thyroid stimulating hormone that triggers your thyroid to release thyroid hormone and growth hormone and things like that. When you see somebody who has like gigantism, for instance, like if you look at like Andre the Giant, right, very famous, someone who had gigantism. He was a big dude. I mean, he was an exceptionally big dude, and that's because he had a pituitary disorder where basically he had a growth that was constantly pushing on his pituitary gland, so his body was constantly releasing growth hormone. Check this out. Here's him holding a beer can. That is insane. That is a huge human being, and that is just because like he had an overactive pituitary gland.
Isn't that what made him pass away?
Yeah, a lot of times gigantism does cause people to pass away at an early age, because your body just can't really deal with the forces of gravity and other things. So honestly, I'm probably going to end up just leaving this as our single note here. You do have thyroid gland. Actually, you know what? Here, we'll go like this. We'll go thyroid glands. These are helpful. Thyroid glands help regulate metabolism and metabolic rates. You've got adrenal glands, which secrete fight or flight hormones, right? Epinephrine, for instance, or synthesizes adrenaline. And then we've got your testes and adrenal glands are also both going to produce things like testosterone. And so like testosterone, you're gonna see, actually says 10 times here. That's funny. It's often 10 to 20 times. It's way higher than that. You've also got your pancreas, which is going to secrete insulin and glucagon. Insulin lowers blood sugar by driving sugar out of the blood into the body's cells. And then you've got glucagon, which is releases glycogen from stored carbohydrates. Releases glycogen from the muscles and liver. Stored glycogen, that's what I should say. I was like, I just don't like that sentence. Releases stored glycogen from those areas, right? And we know that like insulin's great because like that, make sure that we use all that carbohydrate that we brought in. We know glucagon's great too. But we want to make sure that like we're having proper levels of these things. If your blood sugar gets too low, you start to get hungry and you tend to overeat. If your blood sugar gets too high, you tend to have a big burst of energy, and then you burn through all that energy, and then it triggers you to want to overeat. So exercise is great because it enhances our body's utilization of glucose. When we perform exercise, our body goes, oh, I'm going to use that glucose for energy production. So it uses it as like a necessary tool. Epinephrine is like I said, it's adrenaline. It can do things like increasing your heart rate. It can actually elevate your blood sugar levels by epinephrine triggers the release of glucagon, and it opens up your airways as well. And so we got to remember that exercise is a fight or flight autonomic response. And that's great and all, But it does mean that we need to calm down at the end of our exercise. And this is one of the reasons why a cool down is actually so important. So testosterone, right, is a very anabolic agent. It's very good for triggering cytokines to build up your muscular system. Estrogen is also anabolic, but it is not quite as significantly anabolic. Cortisol is a stress hormone. That's actually very catabolic. Growth hormone, also very anabolic. Thyroid speeds up your metabolism. And we know that exercise can elevate literally all of these things. So we want to do that, but we do want to make sure that we watch how much stress we are creating because we don't want too much of the cortisol. And that's really our whole conversation on hormones there. So summarizing everything up, 3 components of the kinetic chain: nervous, muscular, skeletal system. They work to, produce movement, control that movement, and give that movement something to manipulate. Your nervous system is billions of neurons that are communicating throughout the body. Your skeletal system gives you a framework, and your muscular system has all the contractile elements. And that is that. How you feeling? That was 3 days of lessons in one day. How you feeling, Raul?
That was good. I mean, it was like an overview of everything we kind of went over it, but
totally. A couple little extra details.
Yeah, a couple little extra there.
Yeah.
Like we described the Z line.
Yeah, absolutely, right? So we're actually going to see this lecture. You'll see this PowerPoint probably about 4 times before you end the program. So we're going to come back to this all the time.
Okay.
If there was something that you missed, we just look at it from like a slightly different perspective. Like this, section, I talked a lot about like, I mentioned posture a few times, but I mostly spent time talking about like the cells. Next time, we'll probably blast through the cell stuff really quickly, but spend a lot of time talking about posture. And that's because next mod is the posture mod, So there's kind of a different flavor each time. And they're all chicken breasts, but, different spices.
Just trust the process. Trust the process.
Yep. Do you guys have any questions today?
No, I think I'm good. I don't know. Irene?
Well, cool. So tomorrow we got our, wait, what's that?
No, nothing. Just awesome, like knowledge, information that I gained.
Yep, you
Grateful.
nailed it. So tomorrow we've got our midterm. It's going to cover everything we've talked about for the last few days. And it'll be 30 questions. 15 of them will be from homeworks 1 and 2. So you'll recognize 15 of them.
Okay.
And then the other 15, you won't recognize the words, but you'll be like, oh, I know what that is. Like we talked about that. That's just a reworded version of that first question from homework 1. And we'll play a little bit of a review game tomorrow morning, and we'll do it at night, where basically we log in, we go into this website called Quizzes, and it's a little cell phone game where you'll actually play and try to answer all the questions from homework 1 and homework 2 again. But you're going to play against your classmates and like see how high a score you can get. You get more points for going faster, and you get points for being right. And it's just like a fun little competition, and it gives me a way to like look at all your questions, and then I'll go through and answer why. Like I'll be like, okay, so here's what was the right answer, and here's why it's the right answer. And it just gives me what I know I need to talk about, and then we can answer any questions that you might have, and then we'll wrap it up and get you on to taking your test.
Nice.
Cool. All right, I'm gonna go ahead and end the call, and I'll see all you guys tomorrow.
Have a good day, Brad.
All right, see you guys.